meeting is being recorded.
There we go. Recorded it is. Okay, so it just turned 4:55 on my clock anyways. Welcome to everybody. This is the fourth and final, call it ultimate, session of the Atmosphere Ocean Climate Dynamics sessions. I hope that you've enjoyed the other three leading up to this. This is an atmosphere heavy, I think it's entirely atmospheric, hopefully, portion of the AOC Climate Dynamics. So without further ado, why don't we get started on talk about St. Lawrence River Valley fronts, dynamics, thermodynamics, and all sorts of good stuff from John Jackham. So go ahead, John, and I will warn you with 2 minutes left, all right?
Okay, Ron, I've got to share my screen. Okay, let me just do that.
Go for it.
Go right to my talk, put it on full screen, and then we can start the meter. Here we go. Can you see me and hear me okay?
Yeah, the meter's already started.
Oh dear, okay.
Nothing is free.
There's always a cost. Okay, anyway, so my talk today is the St. Lawrence River Valley front. And I would like to acknowledge my co-authors, namely Julianne Ray, who happens to be sitting next to me here. In case if I need to answer any questions, she'll be here. Whose work actually is dedicated to her master's thesis, along with input from Yi-Chen Lo, who's my PhD student. So I'd like to point out and acknowledge NSERC and also the Canadian Foundation for Innovation in this work. Now, this very first slide has some content to it in the sense that it shows you an orographic elevation map that surrounds both YUL, which is Montreal, Quebec, and Burlington, Vermont. You'll notice that here the dots, the big ovals, represent operational sounding sites. And we don't really have any operational sounding sites embedded within the St. Lawrence River Valley. The square that you see here happens to be one additional site that we added, namely the Galt Nature Reserve, which has been recently deployed. And this is identified just to the right of Montreal. So our motivation here is that the St. Lawrence River Valley's orographically enhanced frontogenesis augments precipitation throughout the year, as has been discussed in many previous investigations. In particular, I would like to point out one figure taken from Milrad et al. 2013 in their studies of extratropical transitions that migrated into the St. Lawrence River Valley. And the point that I'm trying to show here is that generally speaking, the heaviest rains tend to be focused right along the St. Lawrence River Valley and not positioned uniquely either left or right of the extratropical transformation track, as would be the case in level terrain. Alyssa Razzi in 2012 showed the bimodality of winds, surface winds, in the St. Lawrence River Valley, among other investigators in the past as well. So primarily, right along the valley, the winds are either northeast or southwest. So our scientific objective here today is to determine the unique synoptic and mesoscale and dynamic thermodynamic structures of the SLRV front. This will be among a lot of future work as well. We'll only get to touch base a little bit on this. In terms of the utilization of surface data from both Montreal and Burlington, we are using the NOAA Integrated Surface Database Station to define a climatology throughout the years from 1979 to 2020. And we're defining a front here as being a contrast between the temperatures between Burlington and Montreal. And using this metric, basically extreme observations being above the 99th percentile, we wind up getting a threshold of gradient temperature contrast of approximately +7 degrees Celsius per 100 kilometers, which is quite a strong temperature contrast considering the proximity of the two stations with each other. Now, we basically, having defined the front based upon this extreme, we identify one particular subset that is surrounded here in a red of relating to warming at Montreal, and this mimics somewhat the ending of a strong temperature contrast with the passage of a warm front. And we're going to be showing later on today in this talk just a recent example, a very recent example from February 2022, which happens to be a representative case of this particular subset. So just a little bit of a review on frontal dynamics. I'm showing you here a rather idealized depiction of an XY coordinate system, a flat map, if you will, of frontogenetic forcing related to winds coming in from the north in the cold air and winds coming in from the south in the warm air. And this produces a confluent non-divergent flow in which the axis of dilatation is perfectly aligned right along the isotherms. And this represents the optimal configuration for frontogenesis. Okay, so the next figure indicates the Q vector formulation, just a bit to show you a bit of a review here, in which we have as an alternative, an update to the traditional Sutcliffe formulation for the quasi-geostrophic omega equation. We have forcing for ascent being driven by the convergence of the Q vectors, with the Q vectors being defined here. Now, perhaps a more elegant representation of the Q vector is indicated on the top line of this particular figure, in which the Q vector itself is defined as being the Lagrangian change of the horizontal temperature gradient following the geostrophic flow. The geostrophic frontogenesis function may also be expressed in terms of the dot product of the Q vector and the horizontal temperature gradient. So if the Q vector, for example, is pointing towards warm air, that indicates forcing for geostrophic frontogenesis. So now what we have in front of us here is a rather complicated array of maps and depictions of the St. Lawrence River Valley front using this subset of Montreal warming events. We have on the left side sea level pressures and 1,000 to 500 hectopascal thicknesses. And we see basically this little trough of warm frontogenesis that's aligned off to the east of this low that's centered off to the north and west of Montreal. The middle figure represents a layer average, the lower tropospheric layer, from 900 to 975 hectopascals of frontogenesis in the St. Lawrence River Valley. And you'll notice here in particular that the focused frontogenesis is right aligned along the St. Lawrence River Valley, as opposed to the much larger scale depiction that we see here on the right, in which the Q vector convergence indicated in the red areas here are directly associated with strong amounts of warm air advection in this layer. As well, we have a broad region of Q vectors pointing towards the warm air, which is frontogenetic geostrophically. Now, the bottom panel actually shows us that among these 26 cases, 23 were precipitating, and yet 22 of 23 were actually maximized with precipitation at Montreal as opposed to Burlington, suggesting strongly that there is the air parcels are ascending in association with a thermally direct frontogenetic circulation, and the ascent seems to be maximized over Montreal during this depiction. The expected wind channeling here is seen for this 26 case composite. In particular, for Montreal, we have geostrophic winds that are coming in predominantly out of the south, and yet at the same time, these observed surface winds are coming in from the north-northeast, exactly like Resi et al. Had shown and exactly aligned with the St. Lawrence River Valley. Burlington geostrophic winds, this is the station to the south, has southwesterly winds with channeled flow predominantly from the south. Now, the time section here, this is from a recent case that we took during Wintry Mix, which is an international field program. This is the utilization of our recently deployed sounding at the Galt Nature Reserve, just to the east of Montreal. And the vertical, section goes from about 990 hectopascals to about 800 hectopascals. We see isentropes and temperature fields, which are indicated in red contours. The shaded blue area indicates cold air, and I define cold as being temperatures of 0 degrees C and less. And what we're doing here in this time section is going to later times from right to left. So this effectively mimics an actual vertical cross section from south to north, left to right, indicating the cold air is concentrated to the right in the north. What's very interesting here is the existence in the frontal zone. It's a very shallow frontal zone with a very shallow layer of cold air, northeast winds, and a very gently sloping frontal zone that caps the cold air during, in fact, a very significant freezing rainstorm with temperatures above the frontal zone, well above zero, upwards of +6 or so, around 890 hectopascals, with a strong southerly low-level jet with 50+ knots of wind in an area of warm air advection. This resembles the type of cross-section that we would see from south to north. Now, just below this cross-section is a time series of 2-meter temperatures that we see at Gault. And the illustration of this figure is such that we see gradual warming that occurs throughout the event. And just after 0400 Greenwich Mean Time on the 23rd, the temperatures finally rose to above zero at the surface. Now, the interesting thing about this is that you might say, well, what's going on right at 0400 from the cross-section? And the answer is that the actual level, the 0 degree level, was well below the first observation taken from the sounding. And as it turns out, the actual freezing level here, or a level of 0 degrees Celsius, was only at about 21 meters. And so that's obviously above the 2-meter temperature readings that we're seeing here. So it's very, very shallow cold air, increasingly shallowing during the event. And finally, I guess around 5 a.m., everything warmed up to about zero. A
minute or two left, okay?
Thank you, Ron. I'm at 11 minutes and 25 seconds. The left panel at here indicates the horizontal temperature advection indicated in red at 850 hectopascals. The blue square, or the yellow square, is actually the location of Gault. And so we see actually much of the frontogenetic forcing is well to the north here at 850, and embedded in a lot of warm air advection. And the WPC map here, the Weather Prediction Center surface map, clearly shows the warm front off to the south with surface temperatures in the upper teens Fahrenheit, and just below the Canadian-US border, temperatures in the mid and upper 40s Fahrenheit. So there's clearly frontogenetic forcing with a migration of the warm front successively poleward. So to summarize, we've identified 4 distinct categories of frontal events. In particular, the recent case of our St. Lawrence Valley front during February of 2022, a wintry mix IOP5, has a very similar structure to that of the 26 case composite of the Montreal warming events. This frontal case that is documented by soundings reveals a shallow frontal zone extending aloft initially to about 253 meters, with much weaker stratification aloft, facilitating actually moderate freezing rain during all this time period. And the 0 degree line ultimately descended to only about 11 meters above the ground 6 hours later. So now future work is to examine dynamic thermodynamic structures associated with frontogenetically forced near surface baroclinic zones in the valley, and the examination of associated precipitation rates and types, along with subsequent physical details of the life cycles of the fronts. So with that, I'll stop and address any question. Here's our reference list. Thank you.
Great, thanks, John. Do we have our questions normally on the chat, or do people raise your hand if you have a question or type it in the chat? I have one kind of methodological question. So you could also have I mean, 7 degrees isn't enormous, right? Some of that could be diabatic as well. It didn't seem like you had a diabatic term in your frontogenesis equation.
No.
Is it possible that some of these cases are really a gradient in cloud cover more than a dynamically generated front?
Yeah, it's certainly possible. I think most of what we've been studying, of course, are wintertime cases in which diabatic heating is relatively unimportant compared with the adiabatic surface wind flows.
Okay. I mean, okay. The precipitation suggested that maybe as well, right? That Burlington had cleared out, and that was why Burlington ended up a whole lot warmer than Montreal. But I mean, the precipitation gradients could be associated with.
I certainly agree with that. Yeah, that's certainly plausible in the wintertime when it does clear out some.
And I mean, I guess with the observations, you could probably figure that out pretty quickly, right? You'll know.
Yeah. Now remember, I mean, the depiction that I mentioned, the idealized depiction is adiabatic, and certainly it's not the case that we're going to be ignoring diabatic effects. In fact, one of the potential diabatic effects that mitigates cooling associated with freezing rain is latent heat diffusion, for example, that occurs when it rains heavily and you have freezing occurring that releases latent heat. And among the interesting scientific questions here is to examine the role of this process and how deep it might be going in a very shallow inversion.
Nice. Did anybody else have a follow-up, or gonna move on? All right. Guess people have had enough time to formulate the questions, so why don't we stop the screen share and we will jump on to the next presentation. I think, if I remember right, that we're going to move from the St. Lawrence Valley, this is why I love CMOS, to Iran, I believe. Is Jeff Safari? Yes. Oh, excellent. I probably butchered your name. My apologies, but I'm looking forward to hearing this presentation. This is definitely a totally different part of the world. So I'll give you a warning in about 10, 11 minutes to have a couple of minutes left, right?
Okay, thank you. Can I share it? So everyone can see it. Thank you.
Not yet. This looks better. Great. Yeah, it's not your first slide, but we see your screen, so that's good.
Okay, thank you.
Can I get you to go into full screen mode?
Sorry. I don't know what it's a effect of the new technology. If you touch anything, it's completely gone. Okay. It's a case, it's my lecture.
Sorry, we still don't see your screen.
Oh,
we saw it and then it disappeared.
Can you see it?
Not yet, no.
Oh my God.
So one possibility would be to share your desktop and not share the...
Oh, now it's in presentation mode, right? Yeah, maybe the desktop's a good idea.
No, it's still, you can't see it?
We can see it, but it's in presentation mode. So it's like half on the next slide. You know what? Why don't we just go ahead with that? I think it's readable.
Jeff, if you can go to play from start in your PowerPoint window, that would be.
Oh, okay.
Okay.
Yeah, if you can click on slideshow. Yes, there we go. Thank you.
Don't touch anything else. And you have 2 minutes left, so.
Okay, thank you. Excuse me.
I'm just kidding.
Okay. My presentation is about a case study of a FOIN event over the Alborz chain mountain in Iran. Before start the main part, I just explain a little about what's the foreign wind. When cold weather, we have on the wind side, and on the leeward, we have a warm dry air. It's named foreign winds. There are four mechanisms for creating foreign winds. In the first one, we have a cool moist air blocking, and then potentially warm dry air passed over it, and it's coming downward from the leeward. So in this condition, we have not any precipitation. In the second one, the cold moist air going upward, and we have precipitation. On the other side, it's a warm, dry air. The difference between A and B is the precipitation. Mostly in the reference book, they told about only these two. The third one is the when cool moist air is going upward, but mixed in the heavy turbulence with the potentially warm dry air. And on the other side, warm dry air is going up, down. And the difference between 1A and C is the heavy turbulence that we have, and D is the mix of all of them. So case to case is different. For example, maybe some case we have here with no precipitation, sometimes with precipitation, sometimes with radiation, sometimes with turbulence. So the difference between the origin of it. Our case study is Iran. This is the world map. If you see, it is Iran, Indian Ocean, Atlantic Ocean, Pacific Ocean. This is Eurasia and Africa. And Iran is here between the Persian Gulf and the Caspian Sea. It's a boundary of Iran. And the area, if you pay attention to this map, you can see that mostly Iran is a high plateau. It's the elevation of the average elevation is 1,500 meters. Here, you can see the case area that I studied. It is around the Caspian Sea here. This wind side, the windward is the mountains that normally the height is in the top is 4,000 meters, and the stations are about 1,500 meters. But on the leeward that the foreign is happened, you can see that if you pay attention to the legend, they are below zero, minus 22, minus 24. And the main station that I worked on it was rushed minus about 9 meters. So maybe it is the only place in the world that the coast area is under the sea level. Here is the forest and the foreign wind in the winter when all parts of Iran is under the heaviest snow and rain. This area is has a very fair winter, and this foreign wind sometimes can cause wildfire, and we have bad fire in the Hyrcanian forest that is here. Caspian Sea is maybe last part of the Titus Sea from the dinosaur times. It's remained. There are the stations that I show you before the Rasht airport, the longitude and latitude of the Rasht airport, and you can see that the heights of it is about -9. When the others, we have stations that is -23, -24. But on the other hand, on the other side, we have some stations 1,500. This huge difference between the leeward and windward make the foreign wind very, very strong, and that's why they can cause wildfire in the winter. For these stations, I use the data such as surface temperature, relative humidity, pressure, wind speed, direction. And so I use the Iranian Meteorological Organization data. And at the final, I use the synoptic analysis from the area. The period that I studied is the period that sometimes we have wildfire at this time. The period that is about 10 of January 2021 until the 10th of February of 2021. That's why I select this time, because in this period we have 4 conditions of foreign wind. The blue line is the temperature, and the red line dew point temperature. For foreign wind, we should have increase in temperature and decrease in dew point. Simultaneously, we have wind speed. That's why in this time, excuse me, in this period, we have 4 events, 4 foreign winds events. But I select this one because in this period, in this the first one, in a very small, less than 24 hours, we have 2 foreign winds, one after the other. You can see that we have increase in temperature, decrease in dew point, and increase in wind. Then the temperature is decreased and dew point increase, and foreign wind disappears. After a few hours, again, the foreign wind started because the difference we have increase in temperature, again, decrease in dew point, and increase in wind speed. So it's a very interesting. As I studied, I couldn't find any similar things, for example, in Alp mountains or in Rocky Mountains, that at less than 24 hours, in a few minutes, we have 2 foreign winds, one after the other. The time series of pressure showed that for all 4 conditions that I studied, we have decrease in pressure from 1025 until 1005, and I mentioned that the elevation here is below the sea level for the station that I studied. The station is the Rasht. If you see, you can see that the chain mountain is like a horseshoe around the Caspian Sea. This part and this part are completely different. This part is Mediterranean weather, and this part is semi-dried weather we have. And because of this mountain and the foreign wind here, we have a very fair winter, while in the east side of the Caspian Sea, the Karakum means the black stone desert, that you can see that it's a very harsh area. The 4 event, 14 to 15 January, 18 of January, 28, 29 January, and 5 of February, the foreign condition was happened. This is the wind rose of the Rasht airport for the 10 of January to 10 of February. You can see that this is the calm weather. Here we have a southerly harsh wind that causes foreign winds. The wind rose for these 4 foreign winds one by one. We can see that if we omit the calm weather, we can see that we have a southerly foreign wind, or southeasterly or southwesterly foreign wind, and at that time, for the other one we have here, harsh wind, foreign wind, and for this one. For this 4 time period that I worked on it, we have southerly, southeasterly, southwesterly wind during foreign condition over Rasht Airport station in all of them. For the foreign event 14 to 15 January that I studied about, you can see that only in 30 minutes, we have a sharp difference in wind direction from north to southerly winds. in only 30 seconds. And wind speed increased from 0 to 5, while temperature sharply increased from 8 to 22, near three times more, and dew point dramatically decreased from 8 to -7. This is the first point winds that was happened in only 30 minutes. And in the time period from 13 to 16 of January 2021, you can see that the temperature decreased sharply from 13 to 25, while the maximum speed, wind speed reaches to 8 and 10. And the direction change from the almost from the north is going to south, and the pressure decreased from 1010 until 1005. It is the 5 hectopascal map. This is the pressure.
Couple of minutes left.
Okay. I only discuss about the first one and then going to the conclusion. This is the 5 hectopascal. The trough is going to the east, and when it is reaching to the study area, the second point wind was happened. This is the map of the 14th and 15th of January, the surface map, and you can see that 1008 and 1016 isobars are near each other. Then at the 22 to 23, we have changing in wind direction to the westerly, decrease in wind speed, decrease in temperature, and increase in dew point. At this condition, point wind disappears. Then again, at the 4:30, really the next thing until the 5, we have wind direction again southerly, while in this time wind speed is remained 2, but the temperature increased from 7 to 14, and dew point from decreased from 7 to 2. It's really for all of them, they are similar to each other. The position of the trough caused the second foehn winds and the Alborz chain mountain, and the foehn event continues as long as this pressure gradient would have existed, as with changing the position of the upper trough, and as a result changing the position of the low pressure over the Caspian Sea, or even high pressure over the south of Alborz mountains. The pressure gradient could be also be changed, really decrease, and then the condition for the foehn event be weakened. Windrows plots confirm shortly southerly and southeasterly and somehow southwesterly wind during foehn conditions over Rash Airport. In conclusion, on the synoptic scale, the foehn events occurred due to the presence of the low pressure over the interior region of Iran and Lee cyclone over the southern Caspian Sea with a strong south-north pressure gradient across the Alborz mountains. When a trough is approaching the Caspian Sea and crossing over, it could change the meteorological conditions north and south of Alborz mountains, causing a simple foehn event over the northern coast of Iran. And last, it's an interesting case, pressure variations with approaching a trough to the study area, and its position with respect to the Caspian Sea reduced and again created foehn conditions over the north of Alborz mountains. As I mentioned before, I couldn't find the similar things, that two foehn conditions happening in less than a few hours. Thank you.
Excellent. Thank you very much. Can I just, I'll make a note to the people studying the St. Lawrence River Valley that you said there were 4,000 meter mountains, is that right?
And the top of the mountains is about 4,000 meters, but the plateau of the Iran is 1,500 meters. So the cities are almost in the elevation more than 1,000 meters. For example, the capital Tehran is 1,200 meters. But the other side, which is Caspian Sea, is below the sea level, -22, -24.
Okay, so do we have any questions? Again, hands or in the chat. And if it's in the chat, Maybe somebody could alert me. No. Okay, well, I had a quick question. So it's hard to sometimes diagnose downslope winds without a radio sonde. Do you have a sounding station close by that you could identify?
The nearest radio sonde for the station was in capital Tehran, so I didn't use it because it was not so near to the area that the point was event. It's about here. The radio sonde of the Tehran airport. And here we have lots of agricultural meteorological stations, but they didn't record the event. Only they use it for agriculture. And that's why I couldn't use the radio sonde of here.
So then just a really quick follow-up, John, I see your hand up. I'm going to get this wrong. The CP Rood Valley, is that large valley just to the south of where your arrow is there? Is it possible that you're seeing a gap flow through that valley?
Yes, this is a gap. Yes, excuse me. This is a gap between the area of the Caspian Sea and area of the Iran Plateau. And here in this gap, we have a harsh wind. It is named the Manjil Gap. And here there are lots of wind farms here, windmill farms here that produce energy from the wind, because every day we have a strong wind in this gap. And in this gap, yes, it could make some effects up here, but it is not too near that I can say pretty sure that it has effect on the station that I studied.
Okay, great. John, do you want to?
Yeah, I guess I'll try to do this quickly, but I know, for example, in North America, when we do have such phenomena occurring, the winds the downslope winds are oftentimes very, very strong, in some cases upwards of hurricane force. And I'm just wondering why in these cases, the wind speed increases seem to be so modest as compared to what we see in North America.
Because in North America, in the west side, you have the Pacific Ocean. And then the Rocky Mountains make it more stronger. But here in Iran, until you have until Mediterranean Sea, you have here in the west of Iran. This is the Mediterranean Sea that caused the precipitation of Iran here. And until it reaches here, it passed from the Mesopotamia or Jordan, Syria, Iraq. And when it is coming, reaching Iran, it's not too strong like the Pacific Ocean's current that reaches to the United States.
Okay. Great. Thank you very much, Jeff. That was interesting and definitely a part of the world that a lot of us aren't super familiar with. Great. So I think, is it Syed next? Is that right? I should have this up. Is it Syed? No, it's Jonathan Buffett. Is Jonathan in the house?
Yeah, I'm here.
Oh, perfect. Okay, great. So why don't you go ahead and start sharing? And I think, where are we at? Coastal heat wave. Okay, but probably not in Iran. So we'll switch geographical locations yet again.
Yeah, it's related to coastal heat waves, or sorry, to heat waves, I guess, but in Eastern North America.
Great.
Can you see my?
Not yet.
Screen. What about now?
It is coming, I think. Yep, it's not full screen yet, but we can see it.
Okay.
Great, and I will give you a warning at 11, let's say 11 minutes.
Yep.
Great.
Okay, so my presentation is about a thermal low in eastern Nova Scotia on Cape Breton Island, and how it interacts with the complex geography that's in the region, especially in the warm season when we have sea breezes and a huge difference in temperature between land and sea. And the data that's being used for this case study is from the Cape Breton Mesonet and the HRDPS high resolution model to compare it with as well. So Mesoscale low pressure areas and thermal lows, they can cause some kind of interesting things to happen, especially when it comes to complex terrain. And this example here is from the BC heat wave in 2021, where you can see in Quileute, Washington, there's actually a land breeze coming off the northwestern side of the Olympic Peninsula. And so we have a thermal low coming in from the south, and that's actually drawing in cold air from the south and hot easterly flow ahead of it. So you can get some really interesting things that happen in those circumstances. And in addition to the standard government network of weather stations, higher density mesonets are able to really show what's happening in finer detail on the ground when these really anomalous events happen. So moving back to the East Coast, so Cape Breton Island is in eastern Nova Scotia. It's not a place that gets extremely high temperatures very often, but when they do occur, you're generally going to see a sea breeze front come in, and additionally, the island of Cape Breton is fairly unique in its topography and the surrounding bodies of water. So I first expected, now this was years ago, but I really first expected sea breezes to come in from either the northeast or the east when we have a westerly flow. And this was when I was much younger and really starting to learn and pay attention to the weather in that area. But this is not actually what happens in reality. So what actually happens is more like this, where in a westerly flow, you actually have it extends nearly to the very far eastern end of the island around Sydney. And so the area of interest is Sydney Bight, which is technically just a bay. But yeah, what always happens is that the sea breeze comes in from the northern side of the bay, the northwestern side of the bay, and works its way south and southeast, rather than coming in straight from the east or even straight from the northeast. And so the two areas that I've highlighted here are Ingonish and Sydney. And this, yeah, this is not the exception. This is the rule. This is pretty much always how it happens. And often the sea breeze won't even make it into the Sydney area, but if it does, it's delayed. So it might be late afternoon or in the evening. So the case study here is from June 19th, 2020. There was a huge heat wave in the area. Anyway, just to add a bit of context to this, I'm not the first one who has been puzzled by the interactions of the sea breeze in this area. So back in the 1960s, the Department of Transport actually attempted to find some kind of correlation between land and sea breeze patterns at Sydney Airport. And the study actually was not successful. And they said that the occurrence of sea breezes are actually rarer at that location than other places with similar topographic features. So the case study is June 19th, 2020. This was a perfect mixture of all the right ingredients. Very rare to have this happen, especially in June. So 850 millibar temperatures were around 20 or 21 degrees. Really warm west-northwest flow aloft out of central Quebec, downsloping into Atlantic Canada. And a well-mixed atmosphere with westerly flow at the surface. So there really was no influence from the Atlantic Ocean. And full sun for the whole day. And we had maximum temperatures 34 to 36 degrees in the most favorable areas. So I'm just going to take you through, quickly take you through hour by hour from about 10 a.m. to 10 p.m., showing the evolution of the sea breeze front and how it kind of turns into a thermal low through the day as temperatures become extremely hot. So it's kicked off in the morning off the eastern side, or sorry, the northeastern side of Cape Breton. So this wake trough had been there all night, even though there had been a fairly strong west-southwest to west flow. And from there, it, as usual, began working its way south as the temperatures increased very dramatically. Now in eastern Cape Breton, the far eastern tip, westerly flow is still going there. Along the southern coast, the southwesterly sea breeze from the Atlantic Ocean begins to intrude as it usually does. And this is just a comparison to the HRDPS, showing where this low is, and also on the mesonet. So what you're seeing is temperature in the circles with the wind direction, and all these stations are set up across the island. And the progression of this sea breeze front. So it continues working its way south, and but not really on the eastern side of the island, except for that one station there. And again, this is the classic setup that always perplexed me. I could never figure out why this happened the way that it did. So as temperatures continue to increase, the low, turns more into a thermal low, like a true thermal low. And on the northern side of it, you've got northeast winds coming in and pushing up against the eastern side of the Cape Breton Highlands, where you see cold air damming. And that's actually going to further enhance the sea breeze front as the day goes on. And again, at the far east side of the island, very high temperatures, offshore wind in a westerly flow. Doesn't really make a whole lot of sense at first. So this is probably the most interesting part of the day. So this thermal low, it's moved south along the Cape Breton Highlands, and now it's going to move southeast. And behind it, it's pulling in fairly cold air off the ocean, off the bay. The water is about 11 degrees Celsius. And then ahead of the front, it's about 35 degrees. And on the southern flank of the low, the westerly winds are actually pushing right out to the coast and beyond. And then behind it, stations that one might consider further inland are actually in the sea breeze. So I really found this kind of fascinating. And at the same time, you've got an area of high pressure associated with the sea breeze front on around the northeastern side of the island, further reinforcing this east flow above the low and under the high. And so as the front goes through, you see incredible drops in temperature, about 15 degrees in less than half an hour at some of these stations. So I just put the temperature trace there from one of the stations. And in the meantime, temperatures are around 35 or 36 degrees in some of the most favorable areas. And again, another station, Catalone, goes from 35 down to about 20 degrees. And the temperature trace is shown above, and the tabular data 10-minutely below. And also the cold air behind the sea breeze front continues to penetrate deep into the Bredor Lake Basin. And at the same time, it's almost like there was kind of two sea breeze fronts. So that's what I've outlined going across just above the thermal low there. So we've got all these complex processes at work. And then around 7 p.m., the sea breeze comes close to reaching its maximum extent all the way down into the lake. So this is about 80 kilometers from the coast. And the shape of the lake and the topography likely had something to do with enhancing that. And then to the east of there, the low sits drawing in warm air from the west-southwest. Yeah, and that's about where it stops. Progressing, daytime heating is limiting around 8 p.m. And by 9 p.m., we've just got this really stagnant area of cold air over Sydney Bight, and not much of a pressure gradient. So it's just kind of sitting there. And then finally, the sea breeze front dissipates, and we begin to see offshore flow along the stations at the coast. The synoptic low from this high heat event is approaching from the northwest. The cold front is above that, and the cold front comes through Cape Breton about 7 hours after this.
Jonathan, we're a minute or two left.
Yep. So in conclusion, why this happens the way that it does? Basically, the shape of the island being an L shape, and the highlands on the northwestern side of it reinforce this warm westerly flow into eastern Cape Breton. Various regions of high pressure from the Atlantic Ocean, the Bredor Lake, the western side of the island, discourage any penetration from the sea breeze from the northeast. And also at the same time, the high pressure over the northeastern tip of the island behind the sea breeze front also kind of reinforces the easterly circulation that flows outward from the eastern side of the Cape Breton Highlands. Basically just cold air damming that's happening there. And just to show some pressure data from the Maisonette, this is a different day, but you can kind of see where that area of high pressure over the Bredor Lake, the central part of the island, is there. And in my opinion, that probably has the biggest impact on why this happens the way that it does. Meanwhile, you've got westerly flow, again, going right out to the eastern side of the island, and cool northerly flow above it. And that concludes my discussion. Let me know if there's any questions.
Great, thanks, Jonathan. All right, Yichen has a question. Yichen, did you want to talk it out loud, or if you don't have a mic, that's fine. So, how much does the Gulf of St. Lawrence moderate the air mass? How about downsloping? Oh, sorry, and as opposed to downsloping off the highlands.
So it depends on the time of year. In the summer, it can have a moderating effect in the early part of the summer, but in the mid to late part of the summer, it seems to have virtually no effect, just because the sea surface temperatures in the Gulf, especially in the southern part of the Gulf on western Cape Breton, go up to 23 or 24 degrees, and a bit cooler along the Atlantic Ocean. They will max out around 20 or 21 in late August.
Okay. And his follow-up was, how sensitive is all this to the really precise direction of the 850 flow? Does it really need to be?
Yeah, so, well, in terms of making a high heat event in Atlantic Canada, it has to be pretty precise from that direction, so that both aloft and at the surface, there's very little influence from the Atlantic Ocean. But is he referring to in terms of what's happening with this sea breeze circulation? Yeah, in that case, no. Even if there's a southerly flow, or you know, whatever variation of kind of south and west or northwest, the same pattern happens, and especially if winds are light, it can be even more pronounced. But
then Kenneth actually asked a follow-up: is there a similar thing happening in easterly flow at all, or it really needs to be south or southwest?
So yeah, the easterly flow is a bit different because we don't really get hot air masses coming from that direction, and you don't really have that lip per se of land jutting out like you do on the eastern side of the island to support one side of the thermal low, if that makes sense. So in this case, because it tends to sit around Sydney, the northern side of the low draws cold air in, while the southern side draws warm air underneath it, as you would see with any low pressure system. So I think if the land was configured differently, that wouldn't happen the same way that it does.
Then I had one sort of related to that. Is in your case study, you showed that the low actually started up near the northern edge of Cape Breton, northern tip of Cape Breton, and then came down the east coast. Is that typical, or was that something, because here it looks like more you're looking at something forming right in the Sydney area, and there's a high pressure to the north.
Yeah, from the case study, that's typical. That is how it pretty much always happens. Okay. What I'm showing here in front of you is like probably midway through the progression of the sea breeze. Although in this case, the sea breeze never actually penetrated the Sydney area, or if it did, it was only like the immediate coastline. But from the case study from June 19th, I also wanted to show the intrusion of the sea breeze into the Bredor Lake. I thought that was kind of interesting as well. Because that doesn't happen all the time, but in extreme examples like that one, it did.
Then one last one from John. It's good because there's quite a number of moving pieces in all this. How well predicted is this by the high-res systems? Generally,
quite well. However, yeah, if I can go back here. Yeah, generally quite well. It's good with what happens out on the ocean and in the bay area. It doesn't usually pick up on the deep intrusion into the Bredor Lake and kind of that southwestern corner of the bay, like you see here. So yeah, that would be one area where the high-res model doesn't always pick it up. But also the high-res models, as good as they always underestimate temperature in Nova Scotia, especially in high heat events. They just, for whatever reason. And so I think if it had a true understanding how hot it actually gets over the land, it may show more cold air being drawn into the center of the island, like what happened that day.
Great. All right, we have to leave it there. Thanks that was a great discussion. Went way over time, that's okay. Now I think it is Syed's turn, is that right?
Thank you.
Thank you, Jonathan. Syed, you're gonna share and all that? Excellent.
Okay, now share the screen.
Something completely different. This should be, let me see, what do we got? What's the topic today, Syed? Oh yeah, this is different. Height-based coordinate for a global model. Excellent. Great, we can see your screen, not in full screen, but.
Okay, just one moment.
Oh, now we see your presenter mode. Make it go away. Ah, better, good. All right. Off you go.
Okay, good afternoon, everyone. So in my presentation today, as Ron has mentioned, it's a bit different from the rest of what you have been listening to. I'll be talking about our recently developed soundproof quasi-elastic dynamical core for the GEM model with the height-based vertical coordinate. And here's a list of my colleagues who have been contributing to this project. First, I would like to briefly touch on the general concept of soundproof systems. In general, the elastic Euler system of equations form the basis of NWP model dynamical cores. And by soundproof systems, what we imply here are some approximations within the elastic Euler system that filter out the vertically propagating sound waves. The rationale behind doing it, the filtering, is the fact that these acoustic modes are meteorologically insignificant, but due to the speed at which they travel, they can impose severe time step restrictions on NWP models. And there are some widely known soundproof approximations, for example, hydrostatic and anelastic approximations that are, however, often limited in their scope of application because they're limited in terms of certain spatial temporal resolutions where they work. In 2009, Arakawa and Connor they proposed a new soundproofing approach by combining the concepts of hydroelastic approximation and anelastic approximation, and they referred to this new approach as the unified system. And later in 2019, Wojtus and others in their work referred to this unified system as quasi-elastic system, and we believe that this term quasi-elastic better captures the essence of the underlying approximation, and we prefer to refer this system as quasi-elastic as a result. And finally, as I have already mentioned during the title, that our present study is based on Environment and Climate Change Canada's Global Environmental Multiscale, or GEM model. The currently operational GEM model employs a log hydrostatic pressure-based terrain-following vertical coordinate. However, recently we have also developed a new GEM dynamical code that replaces the pressure-based vertical coordinate with a height-based one. And we refer to the pressure-based GEM dynamical core as GEM-P, whereas the height-based dynamical core is referred to as GEM-H. And the ultimate objective is to eventually transition from GEM-P to GEM-H for Environment Canada's operational NWP systems in future, because the height-based core is more stable over steeper orography and is more amenable to highly scalable 3D iterative solvers. We have already published in 2021 a paper on our work on adopting the quasi-elastic approximation within the GEM-P dynamical core. And this present study in that sense is like a natural evolution of our previous work, where we are now trying to extend the quasi-elastic formulation to the GEM-H dynamical. The principal underlying approximation for the quasi-elastic system is that any non-hydrostatic departure in the total density rho from its quasi-hydrostatic counterpart rho tilde is negligible. So in the absence of any physics source term, the prognostic continuity equation, in the Euler system is given by this equation. And the quasi-elastic approximation works by simply modifying this equation by replacing rho by rho tilde, where rho tilde is the density associated with the hydrostatic part of the non-hydrostatic full solution. And what happens is this replacement of rho by rho tilde actually makes the continuity equation a diagnostic relation. And hence we can show by normal mode analysis of the linear S problem that this eliminates the vertically propagating sound waves. If I try to be more specific to GEM-H, the continuity equation is actually expressed in terms of pressure instead of rho. And again, the approximation of quasi-elastic system works by replacing the pressure P by P tilde, which is the hydrostatic component of the pressure. And it is obtained by solving a diagnostic relation, which comes from the hydrostatic relation that is obtained by setting the vertical acceleration to 0 in the vertical momentum equation. In their paper through normal mode analysis, Arakawa and Connor in 2009 found that the quasi-elastic system has the best resemblance with the fully compressible elastic Euler system among all the soundproof systems. And it can accurately capture the evolution of large-scale Rossby modes while preserving preserving the non-hydrostatic effects at the smaller scales. These conclusions of Arakawa and Connor were well supported by the findings of our previous study based on GEM-P and the quasi-elastic formulation in it. And in this study, what we are trying to do is we want to find whether we can accomplish the same with the quasi-elastic approximation in our height-based GEM-H dynamical. And before I move into the results, I would like to just briefly mention that the underlying numerics does not change with the quasi-elastic approach. So from this point onward, I'll be referring to the quasi-elastic version of GEM-H as GEM-QE, and the fully non-hydrostatic dynamical core as GEM-NH. And it is important to note that the final elliptic boundary value problem that is obtained by a process of elimination of variables for the quasi-elastic approximation is slightly different from that for the non-hydrostatic system. The vertical structure matrix contains a non-zero additional column, which originates from the presence of a term involving P tilde in the elliptic equation. And this necessitates an inversion operation to obtain P tilde or replace P tilde in terms of P, the actual pressure. And our tests show that this does not add any significant computational overhead. And in the interest of time, today I'm not going to show any further details on these technicalities, but those details will be available in our upcoming paper. At this point, I would like to present some results to compare the predictions from GEM-NH, the non-hydrostatic version of GEM-H, and GEM-QE, the new quasi-elastic version that we have developed. I will be first showing some results involving some two-dimensional idealized test cases that are quite widely used for testing dynamical cores. These idealized tests are primarily focused at non-hydrostatic scenario. And later I will also show some results for three-dimensional NWP to illustrate the performance of the quasi-elastic approximation in the hydrostatic regime. So the first idealized test case that I'm presenting here is widely known as the warm rising bubble case of André Robert. Here we are looking at the evolution of potential temperature of a bubble within a dry isentropic atmosphere. The bubble starts with an initial Gaussian temperature distribution. And in these figures, we are looking at the bubble that has evolved for 18 minutes of integration, and which is at a quite advanced stage in terms of predictability for this problem. On the left here, we have GEM-NH, the non-hydrostatic control, and we have on the right GEM-QE. And as we can see from these figures, that for a primarily buoyancy-driven flow like this one, the quasi-elastic approximation is capable of adequately reproducing the predictions of the fully non-hydrostatic system. And I would also like to stress on the fact that these results are also in good agreement with what we have found with GEM-P, the pressure-based dynamical core. The next case is again another idealized test case, which is usually referred to as the density current case. Here we have a cold bubble that sinks within a neutrally stratified atmosphere. This case is a bit more challenging than the previous one because here, during certain point in the evolution of the bubble, it interacts with the surface, then it laterally spreads along the surface and forms 3 Kelvin Helmholtz shear instability rotors. And in these figures, you can see the potential temperature perturbation contours after 15 minutes of integration. And we can see that the prediction from the quasi-elastic approximation is virtually indistinguishable from the non-hydrostatic prediction. And both of these predict the position and the strength of these shear instability rotors with equivalent accuracy, and they're in good agreement, actually, I would say, with the published results that are already available for this test case. The last idealized test case for my presentation today is known as the Shar's Mountain case. In this case, the test simulates generation of gravity waves by a constant horizontal flow over a mountain range within a stratified atmosphere. And in these figures, what we are looking at are vertical velocity contours. And we also have the quasi-analytical solution of the linear S problem shown using this solid and dashed line, black lines in these figures. And the colored fields, contour fields are from the model predictions. So on the left, we have GEM-NH, and on the right, we have GEM-QE. I mean, if we look at the structure of the solution from the structure of the quasi-analytical solution from the linear S problem, we can see that the solution is composed of large-scale gravity waves, hydrostatic gravity waves actually, that have deep vertical propagation, and there are non-hydrostatic fast or rapidly decaying waves that remain close to the surface. And we can see from these figures that both the quasi-elastic and the non-hydrostatic dynamical cores are capable of predicting both regimes of these gravity waves without any distortion to them. So based on these results from these idealized test cases, we can safely say that with the quasi-elastic approximation, as far as the dynamical core is concerned, the GEM-H dynamical core does not degrade or significantly, the quasi-elastic approximation does not degrade or significantly affect the GEM-H dynamical core for predominantly non-hydrostatic flow scenarios.
A couple of minutes.
Okay, the final result that I'm going to present today is the evaluation of quasi-elastic based dynamical core for 15-kilometer global forecast, where the results are objectively compared against radio sound observations. We have ran a series of 120-hour global forecast for Northern Hemisphere winter with a configuration that is close to our operational Global Deterministic Prediction System, or GDPS. And here on the left, we have the error profiles for 24-hour lead time, the global error. And on the right, we have 120-hour lead time. We have in red and blue the quasi-elastic and non-hydrostatic results, although they are inseparable, I have to admit. And actually, without going into details, what we can say from here is within a confidence interval of 90%, there is no statistically significant difference between the objective scores that we see between the quasi-elastic version of the model and the fully non-hydrostatic version of the model. And to conclude, I would say that the quasi-elastic approach leads to modified continuity equation, and as a result, a slightly modified elliptic problem. But the associated changes in the informatics scores are modest, and the computational cost change is insignificant. For both hydrostatic and non-hydrostatic scenarios, the quasi-elastic core is found to produce results that are equivalent and comparable to the fully compressible model. One of the benefits of having a quasi-elastic dynamical core is that it can eliminate the necessity for having two separate dynamical cores for hydrostatic and non-hydrostatic systems. And also, it may be beneficial to have the quasi-elastic based dynamical core for data assimilation. However, it needs to be further investigated to ascertain this potential benefit. That's about it. And here are a list of the references that I used. Thank you all for listening.
Great, thanks, Ed. So we can open the floor to any questions. I guess I can ask one or two. Does the QE model still going to require off centering? That's
yeah. At present, we still need off centering with the quasi-elastic dynamical core, both for GEMP and GEM-H. It does not affect that. I mean, it cannot help you get rid of off centering.
Okay. And then another one that's probably going to maybe sound stupid, but it doesn't have any impact on the separability of the problem by introducing this column in the elliptic equation, in the matrix. It doesn't somehow make it a 3D.
No, you can still have vertically separability problem. Although I mean, you have this inversion operation that you cannot avoid, but the problem can still be vertically separated. But also you can, I mean, with a high type coordinate, we ultimately want to use iterative solver. So right. That's not an issue eventually.
Great. Okay, if nobody else had a follow-up to any of that, then Syed, thank you very much.
Thank you.
And why don't we see what's next? I should know, of course. It is Jiang Wang, sorry. Ooh, we're moving to common filters. Okay.
Yeah. Okay. So let me show screen. Okay, can you see the screen?
I think it's coming. Hang on a sec. No, it's me.
It is okay now?
No, it's still me. I mean, it's great because it's me, but it's not your presentation.
Okay, let me.
Now it's cyan.
Entire screen, let me. Okay, I find it. Okay, thank you. Sorry for that.
No problem.
It is okay right now?
Yeah, that's good. Well, it's not full screen yet, but it'll come, I guess.
It is okay?
It's fine. It's not full screen. It's not presentation mode yet, but.
It's full screen. Now I can start?
Yeah,
you
go
can
for it.
click from beginning so we can see the full screen mode.
Oh, okay.
Oh, it's because you were sharing just the, okay. We're back to you.
Okay, well, I cannot. Okay, right now I think it is okay.
It's not full screen, but if that's, yeah, try from.
Yeah, if you can click there from beginning right next. Yes, there we go.
Right, okay, thank you.
Okay, it's still not full screen, but that's fine. I think we just go ahead with what we have here. It's fine. Let's just go with that.
Okay, thank you. My name is Ziyuan Huang. Today I would like to introduce about a common filter on grid to improve nowcasting of 10-meter winds. First, I will introduce about from common filter for station to a common filter on grid, TF1G, and then verification with the EMET, and then finally make a conclusion. There are a few acronyms. CMC is Canadian Meteorological Center. HRDP is High Resolution Deterministic Prediction System. RDP is Regional Deterministic Prediction System. It is 10 kilometers.
Zion, I have to interrupt you because I think you're seeing the full screen and we're still on your slides, on your PowerPoint, editing mode. So maybe get rid of your full screen and just work it within the, yeah, this is it. Okay.
Right now, this is better.
Well, it's still within your editing mode for PowerPoint, but I think at least we'll be on the same slide as you, hopefully, if you don't go into full screen.
Oh.
Like right now we see something titled Introduction Context. It's your fourth slide.
Yes.
Okay, so just go ahead with that.
So go here, okay. And INCS is integrated point nowcaster system. And NWP is numerical weather prediction. And UMOS is updatable model output statistics.
No, sorry, Zion, I think you're looking at slide number 3 and we can only see slide number 4. Not sure.
Right now is going developing nowcasting on a grid, right?
Yes.
Okay,
go ahead.
CMC has a nowcaster system for station locations. These are DPS INCS UMOS integrated nowcaster system used more UMOS and the weather elements on grid V1G projects and the grid products to support the various forecast programs. Nowcasting is part of this modernization to gridded products. Nowcasting of weather elements on a grid NCV1G and developed on the HRDPS national 0.5 kilometers grid. This table shows wind nowcast, point nowcast, whereas grid nowcast.
Yeah, so Zion, sorry again here. We're still not seeing that table. You haven't moved from slide 4 for us. I'm not sure what you're looking at exactly, but I mean, for us, it really is the editing window for your PowerPoint presentation. So maybe if that's what you could use to step through the slides, that would work best.
Okay, so just use normal don't use.
Don't use
okay.
full screen presentation. Yeah, now we're good.
Okay, okay. Okay, then. Okay. Observation for the point nowcast is from station locations. Grid nowcast is from method analysis on grid. And NWP for point nowcast is RDPS 10 kilometer resolution. And for the grid nowcast is HRDPS national 2.5 kilometers. And for frequencies, 1 hour's frequency. And soon, grid nowcast will be 30 minutes frequency. For the post-processing, point nowcast use the RDPS CMOS, but for the grid nowcast is used the RDPS increment. And increment means analysis minus HRDPS at t minus 0 time of analysis. Common filter on a grid to improve wind nowcast. The KF1G project objectives to improve NC-VNG 10-meter winds and start from common filter from station locations. It improves wind forecast and considers wind direction as NWP errors sensitive to wind direction. And then we adapt it to a common filter on grid KF1G. Finally, we evaluate KF1G wind results for NC-VNG. And this figure shows the common filter for station locations. It is a mean absolute error. Let's see the red line. It is the common result of from common filter. If we compare to the green line, it's CMOS, and then compare to NWP, so it's the black line, we can see that point common filter improve jam run to 0.5 kilometers and may bring values to CMOS. And this figure shows the POI's percentage of improvement of common filter from NWP with the number of training days. Let's see from this figure, we can see the common filter with 19 days of training has the biggest improvement from NWP in terms of MAE, mean absolute error. It is red line, and the green line, it is standard deviation of error. And the outperform of CMOS, CMOS is dot lines. And this table shows how to adapt station common filter to a common filter on grid. The observation of common filter based station is from station locations. And for the KF1 grid, it's method analysis on grid. Both of them, NWP is from HRDPS 2.5 kilometers resolution. For the training, KF by station used 60 or 90 days as training. But for KF on grid, used 15 or 30 days as a training. And this figure shows mesoscale surface analysis on HRDPS national grid used observation data where it is available. We have temperature, humidity, and surface temperature, pressure, wind, and wind gust, or dew point, or visibilities. This research we use the wind. So this figure shows the wind speed increment at 10 meters. The blue color shows observation smaller than HRDPS. The red color shows observation bigger than HRDPS. The increment, it is just model error. So common filter works with model error. So there are another kind of increment. For example, TT is dew point temperature. TT is temperature, and the surface temperature increment, and the wind gust increment. And this figure shows the preliminary or common filter on grid verification using EMET. EMET is a verification system used at CMC for point locations. This figure, the left part is options we're setting up, and the right part includes 3 panels. The first panel it is compare models. Here we have 6 models, and the second panel is which first 2 models above score better. We compare 2 models. And the third panel shows how many the numbers of observations used for verification. And this figure shows mock-up of HRDPS and method analysis topography compared to real topography. We know that mesoscale analysis is made on HRDPS surface topography. For the Eastern Canada and prairies, HRDPS is reasonable close to actual topography. For the BC and other mountain areas, there can be significant difference between HRDPS topography and the actual topography. Differences in the topography may help explain some difference in verification scores on next slide. This figure shows root mean square error for the Canada East in the summer and fall. Let's focus on the result from common filter. Red line is used 15 days training, and the blue line used 30 days training. Let's compare it with RDPS Inc. UMOS. It is now point nowcast. This purple line, you can see that the scores close to RDPS Inc. UMOS. And it is better than green line, it is nowcast, and also better than HRTPS, it's a pink line or orange line, and the VNG is a pink line. The dashed lines is mean error, mean forecast error. Common filter is red and the blue line. We can see it's common filter removes much of model biases.
0 minute or 2 left.
Okay. And this figure shows the root mean square error prairies in summer and fall. We can see that common filter red line and the blue line is very close, and sometimes it's better than RDPS Inc. UMOS. And also is better than green line nowcasted, and orange line is HRDPS, and better than VNG is pink lines. So this figure shows the root mean square error for the British BC in the summer and fall. We can see they are almost similar result. Common filter and result is red line and the blue line. It is difficulty approach to the RDPS Inc. UMOS scores. Also is better than green line, nowcasting, orange line, and VNG and HRDPS. So I would like to make a conclusion. Successfully adapt point common filter to a common filter on grid, and the KF1G reduced HRDPS wind bias in all domains. KF1G for the wind root mean square error scores similar to RDPS Inc. UMOS. It is a point now, and sometimes it's better than it. And the poor performance in BC due to topographic effects. And the KF1G in flat structures is modular, good for calculations. We are monitoring performance over a full year. KF1G could also easily be adapted for other applications. A special thanks to WEE for significant contribution in development and our colleagues for valuable help, comments, and support. Thank you.
Good, thanks, Jan.
Yep.
Feel free to question. Yeah. Right. Okay. Chris asks why the NWP topography be more rugged than the real topography. Yeah, that's
okay.
That's right.
This one.
Yeah. Yeah, I mean, it's true that we do apply filters to the orography field when we read them into, when we create geophysical files for the NWP systems. So it's unlikely to be rougher. It certainly shouldn't be rougher than the real topography. But this is just, just an example, right?
Yeah, I think, the difference of computer between for the CMOS, it is due to, I think it's a topographic difference. We will consider of that next step.
Okay, a related one, I guess, technical, in EMET, there's an alt-diff max option that lets you reject stations that have well, co-located stations. One of, in one of the topographic fields, it's more than X meters away from the observation height. So that'll get rid of the problems that you're seeing for British Columbia if it's really just a change in station height. So there is a way to fix that. It's in EMET.
Yeah, we think it is the main reason for difference. Is it difficulty approach? Yeah.
Right, I understand, but what I'm saying is that there is a way to fix that in EMET, so you'll be able to get scores that are reliable. It's called it's called alt-diff max. So if you activate that, you will reject stations where there's different departures from the observed topographic height or station height.
Okay, I will try for that EMET. Okay.
Great, then I have one last one. If nobody else, I don't see another question in the chat. It wasn't clear to me where the covariances were coming from for your Kalman filter. That obviously should have been clear, but I didn't catch it.
Which one?
The Kalman filter needs covariances, right?
Kalman filter
for KF on grid or whatever. It needs covariance, right, to do the filtering. I'm wondering where it gets those covariances from.
Yeah, I think so. But
okay, no problem. I'm sure we can take this offline. So
okay,
great.
Thank you.
Thanks, Yang. And we will move on to the next presentation, which should be it's the last one. All right, Shinli.
Yeah, I'm here.
Great. Then
I will share my screen.
Good. More data assimilation.
Yeah, can you see my slide?
Yep, now we can get it's full screen. That's great.
Yeah. And hello, everyone. My topic today is about the impact of the land data simulation and land atmosphere interactions in the Heihe Basin, Northwest China. I'm visitor student Xinlei He from Beijing Normal University. And we know that the soil and vegetation processes directly affect the land surface energy and water circulation, especially in the arid and semi-arid regions. And up to now, we also have so many land data simulation systems aim to produce the high quality fields of the land surface fluxes by simulating the satellite-based or ground-based observation data products with the advanced land surface model and data simulation technologies. And we know that the more realistic land surface conditions can improve the estimation of the land-atmosphere interactions. So in this study, we try to building up a data simulation system to simulate the leaf area index and soil moisture data into a WRF model and to produce the more robust soil and vegetation conditions. So the purpose of this study is to, the first is to construct a coupled land data simulation system. A second is to simulate the LAI and the soil moisture data into the WRF model. And the third purpose is to study the effect of the land data simulation on land atmosphere interactions. So in this study, we selected Heihe Basin as a study domain. The Heihe Basin is the second largest inland river basin in northwest China. And the left figure shows the elevation changes in the Heihe Basin. And in the south is a very high elevation. And the right figure shows the land cover types of the WRF model at the 3 kilometers resolution. And in this region, we selected 9 sites to validate the model results. And the midstream, we can see that the midstream oasis is especially covered by the irrigated cropland, and the downstream oasis is mainly covered by the riparian forest and the shrubland. So this line is the Heihe River. And this is our proposed the data simulation framework. And we can see that the coupled land atmosphere data simulation system consists of 2 steps. In the first step, the forcing data for the non-MP model was generated from the WRF model, and the meteorological forcing data and initial states from the WRF model will input into the non-MP to simulate the leaf area index, soil moisture, and ET. And in the second step, we constructed the land data simulation system to update the leaf area index and the soil moisture in the non-MP model. And then the updated leaf area index and soil moisture will recoupled to the WRF model to produce the more realistic land surface conditions. And in this study, the data simulation method, we used ensemble Kalman filter method, and the simulation data is about the map, soil moisture product, and glass leaf area index. So this is a select physical scheme about our WRF and WRF data simulation. So in the study, the WRF data simulation framework was run from May to September in 2015. And the WRF model is spun up about 1 month. And in this study, remote sense LAI and the soil moisture were simulated into the WRF model at 0 o'clock every day. Yeah, this figure shows the most average leaf area index and the soil moisture estimates. The first row is leaf area index, and the second row is soil moisture from the WRF data simulation and remote sensing products. And we can see that the data simulation increased leaf area index during the growing season in the summer months. Also, the soil moisture estimates from the WRF model, this green bar, are remarkably lower than remote sensing products, especially in the cropland and the shrubland. I think this is because the impact of the irrigation events and the shallow groundwater table in shrubland is not fully considered in the non-MP model. In contrast, the soil moisture predictions from the data simulation, this orange bar, can improve the leaf area index and the soil moisture estimates. And in general, we can see that the WRF DA data simulation can use information contained in remote sense products to improve the land surface conditions. And this figure shows the spatial distribution of ET estimates from the WRF and data simulation and the ET map. This is our proposed upscaled watershed ET product via machine learning method. So we just list here as a reference data. So the results can see that the results indicate that the ET values from WRF model are underestimated in the Heihe Basin, especially in the midstream oasis region. This is mainly because the WRF model underestimates soil moisture and the leaf area index in this region. But compared to the WRF model, we can see that the data simulation can improve the estimation of ET, and the spatial distribution is more consistent with ET map. We also validate the air temperature and specific humidity results. This figure shows the monthly average air temperature from the WRF and the WRF data simulation and observations at 9 sites. The first row is the upstream sites, and the second row is the midstream sites. So we can see that the WRF model overestimates air temperature in the Heihe Basin, especially in the midstream oases. Compared to the WRF model, the data simulation can simulate the signal cycle of air temperature at 9 sites and are closer to the measurements. And I think this is because the simulation of the remote sensed LAI and soil moisture can improve the estimation of the vegetation dynamics and the soil moisture, and finally, it can reduce the air temperature. And we also validated the specific humidity, and the same pattern can be found in the estimation of the specific humidity. And we can find that the data simulation method can effectively improve the estimation of the specific humidity, especially in the midstream areas. And this figure shows the spatial patterns of the air temperature, the first row, and the specific humidity, second row, maps from the WRF and the data simulation. And we can see that the simulation of the leaf area index and soil moisture lead to a decreased air temperature and increased specific humidity in the vegetated area of the Heihe Basin. We can see especially in the midstream oasis region. And the results show that the data simulation of the leaf area index and soil moisture can make oasis as a typical wet iceland and cold iceland compared to the surrounding desert. And also the 2 rectangle areas, this blue line area, are selected in this study to further analyze the effect of the land atmosphere interactions in the midstream and oasis region, because there have big oasis region in here and a small oasis region in here. And this figure shows the variation of the temperature and specific humidity differences with height from WRF model and data simulation methods. So in this figure, red solid line represents the leaf area in LAI estimates by the data simulation method. The gray dashed line represents leaf area index estimated by the WRF model. So we can find that the wetting and the cooling effect of the midstream oasis are strongest in the southern irrigated cropland in this region and gradually decreased in northern desert areas. And we can see that the magnitude of the first wetting and the cooling effects match well with the difference in the leaf area index and the soil moisture. This can be represented as the difference. So we can also see that at the same time, the wetting and cooling effects of the oasis gradually decrease from the land surface upwards and disappear as at a pressure level about the 600 HPA. And the same pattern can be found in the downstream oasis, but this effect is diminished. And the results also indicate that the wetting and the cooling effects of the downstream oasis are weaker than those of the midstream oasis. Meanwhile, we can find that at the pressure level about 500 HPA, and we can find that a slight warming and drying effect can be found. This effect may be caused by the movement of air mass due to the local circulation, and the airflow from the desert can bring more dry air, and it can increasing temperature and decreasing specific humidity. And this figure shows the wind speed simulation results from the WRF model and data simulation results. And by comparing it, we can find that the irrigation and vegetation growth in the midstream oasis can produce a wind shield effect. And in addition, we can find that the wind speed within the oasis is less than that of the surrounding desert. This is because the resistance created by crops and the residential areas in this region can slow down the wind speed from the desert, and it also can change the wind directions after the data simulation. And we also found that the wind vector in the downstream oasis is mainly controlled by the background north wind. So the effect of the data simulation on the wind vector are weaker. Simulation of this LI and soil moisture not only affect the first wind speed, but also influence the local circulation. So this figure shows the difference of the local circulation averaged in midstream and downstream oasis between the data simulation and the WRF model. And the cool and warm colors represent the decrease and increase of the wind speed, respectively. And we can find that the strong oasis desert interactions can be found. The divergence of the lower atmosphere over the midstream oasis is enhanced in this area, and the wet and the cool air mass is transferred to the surrounding desert, while the more dry and hot air over the desert is transformed into the oasis from the upper atmosphere, about 500 hPa, and in the upper atmosphere from the desert to oasis air mass enhance the background northerly wind, so that we can see that the wind speed is increased in this region, and it can bring more hot and dry air over the oasis region, and which can lead to increased air temperature and decreased specific humidity over the midstream oasis.
1 or 2 minutes left.
Okay. Yeah. This slide shows the difference of the precipitation is calculated by the data simulation minus WRF model, and we can find that the data simulation lead to the more precipitation in the upstream of the Hei-Ho Basin. And this is because the water vapor flux direction is generally from the northwest to the southeast in the Hei-Ho Basin. And after the simulation of the leaf area index soil moisture and water vapor from the midstream oasis can transfer into the mountain regions, it can enhance the precipitation in the high latitude regions. We also selected a very small region to do more analysis, and we also found that the data simulation can enhance the estimation of the precipitation on the windward slopes compared to the valleys. So there are some conclusions here about the data simulation can enhance the wetting and the cooling effects and the wind shield effect. Also, the simulation of the leaf area index and soil moisture can lead to increased precipitation in the mountain regions. Okay, that's all for me. Thank you.
Thank you. All right, we have, I realize that we're over time, but this is the last presentation. So if there's anybody with a question, I had one, and this one I should have caught probably at the beginning, but when you say coupled land atmosphere data simulation, do you mean really that the background error covariance matrix that you're using for data simulation includes both the atmospheric predictors or whatever control variables and the land surface ones? Like simultaneously, you're solving the full, you're using the full covariance matrix, or do you really mean that the systems are coupled?
I do that. And in my coupled system, I run the WRF model, and the land data simulation is a separate part. So we just do the we just run the ensemble Kahneman filter method as ensemble run with a non-MP model as the land first part. So
but do you do that separately? Is that done independent of the atmospheric common filtering, or
it's a separate?
It is. So it's not a coupled. It's not a fully coupled or strongly coupled system where you would use a single background error covariance matrix that includes the land surface variables.
I think it's a strong coupled because the WRF model can provide the forcing data to the land first model, and we also create the ensemble run to run the land first model, and we calculate the Kahneman filter to update the state variables, and then in next time step, the upscaled the state variables will recoupled to the WRF model.
Okay, my understanding in the assimilation community was that a strongly coupled system was one where the background error covariance matrix was extended from the atmosphere into whatever the subsurface was. So then you would have increments that were being generated by soil moisture observations, for example, directly in the 850 millibar temperatures or whatever. That seems a little different from what you're doing, but unarguably you have good results, so that's great.
Yeah. Thank you. I will consider that. Yeah.
Does anybody else have a question? Comment? Okay, then we'll say thank you for that. And thank you to all the presenters in the session. A bunch of technical problems, but you guys persevered and we made it through. So thank you, and to everybody who hung on for the little bit of extra time. I don't know if Adam or Merrick or Mike, you guys had any like final thoughts or announcements that we had to make?
No announcements to make, just to thank everyone for participating and for making this a great session over the last couple of days.
Excellent.
Yeah, thanks everyone, it was great. Yeah.
See everybody in next year's CMOS.